Now, to get the actual longest common subsequence, what we are going to do here is, when we fill this LLCS table, we will be storing some extra information that specifies how each of the term LLCS of S1.I T.J was computed. So is it because we are trying to add 1 to the LLCS of S of 1.I minus 1 Tj T of 1.j minus 1? Or is it due to the larger value that is coming from the left side, or the larger value is coming from the top side? So we are specifying how we obtain each of these LLCS value during the computation. Once we have this extra information, then it will be easy for us to retrieve the LLCS by a process called backtracking. So we will explain how backtracking is done by an example. So here, this is how we fill in the table, but this time we have these arrows that specifies how we get each value. So this one, how do we get a 1 here? It is because it is 1 plus this 0. Okay? Yeah, because these two characters are matching. So when we have an arrow that points like to the 45 degrees to the northwest direction, then in that case, it means that we are matching a character. Now for all these cases, yeah, this is the maximum of these two, maximum of these two. So it is like pointing to the direction that how we get this value from the maximum of which. So this is about the first row. And then for the second row, we can also do this. And then third row, and so on and so forth. So in the end, we can compute this table with the arrows. Now, the process of backtracking is actually simple. So we now know that the last value here specifies that the LCS has length 4. So the 4 here, it says that, oh, it actually comes from the 4 above. So what does that mean? It means that for the LCS that we are thinking, this character will not be used. So we just take away this character. And for this 4, again, this 4 comes from left-hand side. So in the LCS that can give us a 4, then this character is not used. So we can take this away. This 4 goes up, so we can take this away. This 4 goes up, we can take this away. But for this 4, it points to the northwest direction. So that means that we are matching these two characters. So one of the possible LCS is we try to match these two characters and then find out whatever is the best for the remaining part of the string. How do we match dirty with dormitory? So in that case, we find the best way here. So again, we move on according to this arrow. So we find out that, oh, there is another one that points northwest. So in that case, we have another matching character, T here. And then another northwest, the matching character is I here. And we go, and then we go northwest, D here. So using this so-called backtracking, so we go back from the last point that we have and trace back based on whichever the best decision that was made or how it was made, then we will be able to find out what is the best way to get each of the subproblem, and so that we get the corresponding LCS. Okay, so this is the backtracking. So backtracking is rather easy. Okay, there are some extra points. Okay, so suppose that we just need LLCS rather than LCS. Suppose that we just need the value of 4 rather than we want to do this backtracking. Now, an interesting thing here is that we can actually save some working space. So in the current method, we have constructed a very large table of NM entries, right? So we make a very, very large table to begin with. We have a super large table, N times M entries to begin with, and then fill in the values one by one. We are filling the table row by row. But we see that when we fill a certain row, it only depends on the row immediately above it. So what does that mean? So if you go up to this example, when we fill this third row, actually, we just rely on the values here. So the values that is earlier in the above, they are actually useless. So what does that mean? It means that we just need always to keep the two current most recent rows, and then we are able to compute the value of each new row. So when we compute this one, then we have this one. And to compute this one, then this row is now not needed. So we can reuse the space of this one to fill in this here. So what does that mean? It means that if we just, need this LLCS, then we can save the space. We don't need all the NM space. The extra space that we need can be reduced from NM to the number of entries in each row. So in our example, it is order M. But actually, we can have the minimum of N and M instead. So you can think of this as we can fill things row by row. We can also fill things column by column. So if it's column by column, order N space, row by row, M space. So we know whether N and M, which one is smaller. So in that case, at the beginning, we can fill it in the corresponding way so that we use fewer extra space. Now this is for the case of finding LLCS. Now how about LCS? Now in the current method, we use backtracking. And then backtracking seems that we will need to have all the entries, all the information stored so that we'll be able to retrieve the string along the way. However, Hirschberg in 1975, he has proposed a very smart method so that even though we are computing LCS, we can still use only minimum of NM space. Now this idea is we somehow find the best way to divide T into two parts, which could be uneven in length, so that in order to obtain the LCS between S and T, we hope that the first part of T will be matching the first half of S. So for S, it is always half. But for T, it is uneven. Okay. So the first part of T matches the first half of S. The second part of T matches the second half of S. So somehow, Hirschberg find out the cutting point of T that makes it correct. And after this, after finding this cutting point, he will use recursion to also find the cutting point in the remaining part. When all the cutting points are known, then we can retrieve the LCS. So this is Hirschberg's idea. So not very clear here, but if you are interested, so you can search for Hirschberg's trick for this LCS problem. Now to end this lecture, we will mention a related problem called edit distance problem. So here, edit distance of two strings S and T is as follows. Suppose that we have S and T, but here, this time, we want to convert S into T. We are allowed to perform some character edit operations, where a character edit may replace a character of S by any other character, or we may insert a character at some point of S, or we may delete a character from S. And we want to find out what is the minimum number of edit operations needed to transform or to convert S into T. So for instance, let's say we have an example. So let's say S is the word practical and T is the word factual. Now we can convert S into T using 4 edit operations. Now to see this more clearly, we will see, so we will make this following representation. So S is practical, T is factual. So when we see two characters, so they are now, we see that they are now of the same length because we have inserted some extra symbol here. So we will see what is the meaning. So which 4 edit operations allow we convert S into T? The first one is we replace P by F. And next we delete R. And next we replace I by U. And next we delete C. So in that case, after these 4 edit operations, we are able to convert S into T. And then we want to find out what is the minimum number of edits that we need to convert S into T. Now, so for this representation, if we place a character over a character but they are not the same, this means that it is a replacement. If we place a character over a strange symbol, this empty character symbol, then that means that we are trying to remove this character. Now, how to represent insert? Insert is the opposite. So when we have an underlined character here with an actual character there, then that means that we're inserting a character at this location. So this problem is called the edit distance problem. And actually, as a practice for you, we can easily modify the method for LCS for this problem. So we can use the LLCS method to compute the length of the LCS, and here we can use this method to compute the minimum number of operations for the edits. And after that, so this can be solved in order nm time, and also it can be solved in minimum of nm space. So we will leave this for you as an exercise. And finally, if we are able to find out what is the minimum number of operations, then see if you can use backtracking to find out what are the corresponding edits that we need to do in order to get the conversion. So that's all for this lecture. Thank you.